Hi, and Mr. Boxy? Ah, there you are. Are you ready? Looks like it. Great. The topic of this episode is coordinate space transformations. So in this episode, we will first demonstrate how to apply and reverse coordinate space transformations, and after that, we will show a practical appliance of this principle. So in front of Mr. Boxy is a teleportation device, and the computer shows us which transformation matrix is used for this teleportation. So Mr. Boxy, please step on the teleportation pad. Now don't be shy, this is safe. I guarantee you that probably nothing bad will happen. So, are you ready? It doesn't matter, because the machine is ready. Let's punch it. Well, look at you. Everything is fine, and it worked. So, just one minor thing. Mr. Boxy hasn't moved because the teleportation is right now set to, well, not to anything. It's the identity matrix we are applying here. So let's change it a little bit. Looks fine to me, so have a go. There. You see? Everything is fine. We have only turned you around by 180 degrees now, so let's move you actually. There you go. Now here you have moved actually. So the teleporter works. How about trying something more exciting? Now have a look at you. You're so cute now and angry. I understand. We can probably fix this. Just another matrix will do that, right? Well, whoops. That wasn't the right one. Finding the matrix for your current state is not so trivial, but there's a solution, Mr. Boxy. We only need to inverse the matrix that we have used for the teleportation. So on the left side, we currently see the current matrix that was being used, or that is being used for Mr. Boxy. And next to it, we see the matrix that is undoing this. So if you multiply this matrix with this matrix, the result is the identity matrix. So let's feed that matrix into the teleporter. And one more time. There you go. Everything is back to normal. We just have to be careful, because we can't fix everything this way. Because the inverse of a matrix operation is like the inverse of a simple number multiplication. If we take x, multiply it by 1 and divide it by x, the result is 1. And this works with almost all numbers. Just 1 doesn't work. It's 0. Because if we multiply a value by 0, well, all the values become 0. It doesn't matter which value we use, and so we can't restore that information. That information is gone. So let's demonstrate this principle. Mr. Boxy, step away. This test will be dangerous. All that we need is now a suitable test object. Here we go. The octopus will help us here. So now let's use a teleportation matrix that is actually harmful. Now we've pushed the button and our poor octopus test object is now perfectly flat. He is now a two-dimensional octopus. And that is because we took the y-axis and replaced everything with zeros there. And this is a problem, because this column is now 0 and this row is 0. The information on the state of the y-axis is completely gone. We have erased that. And that means that there's no matrix that exists to restore that value, because where should this value come from? It can't reappear from anywhere. Because likewise, there's no number that we can multiply a 0 with to get back the original number of the multiplication. It just doesn't work. So now that the octopus is all flat, we can no longer apply a transformation that unflattens him. I mean, of course, we can make a full reset of the matrix, but we can't find out what his matrix was before this harmful operation. So let's recap. We can invert a matrix to reverse a transformation. When we multiply a matrix with the inverse, the result is an identity matrix. but we can't fix all them and invert all the matrices. Only invertible or non-singular matrices can be inverted. In general, when we lose information on one axis, or we mix it up, or do some other strange operation, we can't undo this information loss. Now, where does this lead us to? I want to give you a practical example. Screen coordinates. So, our computer in Mr. Boxy's world has no control system. But Mr. Boxy wants to control the UI using a laser pointer. So how can we make this work? So here is the screen, and Mr. Boxy is already pointing where he wants to go. And we have a UI system here in place, and it gets rendered in this position. So the UI is attached to the computer, and it is rotated, scaled, and translated in space. Now, the world matrix of this UI looks like this. It's the y-axis goes downwards, so here is 0, 0, and here is 400 and 350. And the z-axis is pointing towards us. Now, Mr. Boxy's laser itself is just a ray. So there's an origin, which is here, and there's a direction, which currently conveniently points to my mouse coordinate. Now, we can use the screen's inverted matrix and convert the ray into the UI's local space. And then it looks like this. So you see there's still the white ray of Mr. Boxy, and I'm projecting the ray now to this plane and to this plane, so you get an idea where we are pointing to, because if we just move upwards, you see this projection here is moving up and down, and the one at the bottom is moving left to the right when I'm doing that. What you can also see is that Mr. Boxy is jumping up and down, and you can see this because this point is moving, whereas the screen itself is static, because everything is now in the local space coordinate of the screen. Now, what we need to do is we need to project this ray onto the XY plane. And this is really simple in local space coordinates, because we are only having to project it onto the plane. And the operation for that is that we take the origin and then we calculate a number, which is the origin z value divided by the z of the direction, and multiply it with the direction. And then we get the projected point. Note, if this value becomes 0, we are parallel to the plane, and then we can't get a projected point, and that explains it more or less why this doesn't work. Now, when we do this, we get a number, and you see down here there's the coordinate on the local on the UI screen. And if you take a look at the numbers, and I've already mentioned it, the screen is 400 wide and 350 units high. So these points, these coordinates here, are already local space in the screen. And that is very convenient and very simple to use then. So now we have everything to let Mr. Boxy control his very own computer. What will he do? Oh, he's playing a game. Well, I think he has deserved it. Now, there are a few other cases for converting coordinate spaces, and when I'm working with it, what I use it for is, for instance, calculating the signed angles of a direction. So I want to know if I need to turn right or left. Another very useful appliance where you need to convert a lot back and forth is making a camera zoom to your mouse cursor. I want to make a video on that because this is very interesting. It's a reoccurring problem, and when you know how to solve it, it becomes a lot more simple. Although I have to say, it is not that simple to demonstrate, and so I want to take the time and make a video on that. Another point, which is very similar to the first one, is determining the control directions of an AI agent. So we want to know from the point of view of an AI agent, what is right, what is left of us, and what can we do with that. Now note that all these use cases can be solved more efficiently with specialized functions. And the advantage of using matrices is that it is a single tool, and this is making things a lot more simple, because when you're working with local coordinates, a lot of problems become much more simple. And this is the case for a lot of transformation functions. So there are a lot of space transformation functions where we take one problem, convert it into a different space, and then the solution to that becomes more simple. And I think this is one of the most basic examples how this can work out. Now for the outlook. I want to take a short break from talking about matrices, and I want to talk about tiled geometry next, and sprites, of course. So when we have a tiled map, I have developed a way how to work with it, which I think is very convenient, very useful to know, and therefore I wanted to give you a tour on what I'm doing there. Until then, please leave a like, comment what you have found useful or what you think, and subscribe if you want to see more. Bye.